All right, so in part 2 of our mammoth session, where we will look at a slightly different topic and talk about the infrared properties of amplitudes and hence QCD and perturbation theory. So on-shell methods is a thing which is typically, depending on your university, not covered, and infrared is definitely something which is usually not covered. It's normally described as too hard, or if you're impolite, more polite, too boring. So you can decide at the end whether it's too hard or too boring. But it's important because it's what we need to do to make a prediction at NLO accuracy, because we have to include both real and virtual emissions together and find some way of combining the two in a way which leaves both free of singularities so we can actually do physics, make some predictions. So before we get into that, I was asked a couple of times at the break whether or not I would give you these beautiful, I'm modeling them here, beautiful notes. Fantastic, I have to say. The answer is, of course, once I finish removing all of the most stupid typos I can spot. So that there's some threshold of which I will happily let other people look at it. They're not quite there yet, but probably by tomorrow or Friday I'll be able to send them around to you. So yes, you will get these. How useful they are is of course questionable. All right, so we're looking at the real corrections now, because we sort of know what the infrared we know what the infrared properties of our one-loop amplitudes are because we know our basis, right? We have our basis. We can expand it out in terms of d, which is equal to 4 minus 2 epsilon. So we calculated all of our coefficients using our clever methods of unitarity or otherwise, and we can expand our basis integrals out, and we get a series in epsilon. So the virtual bits give us something which goes like 1 over epsilon squared plus something else over epsilon plus a finite function as epsilon goes to 0. So these, after UV renormalization, so we assume that we've renormalized all of our couplings and any relevant masses and that sort of thing in the game, these are now infrared divergences. Okay, so this is bad. We can't put epsilon to 0 without blowing up our calculation. Epsilon should be 0 because we want to work in some 4-dimensional problem. So that's the virtual. But we assume that at least we know this, right? We've calculated it using our unitarity. We have an expression for our amplitude. We can expand it. We know the coefficients A and B, right? So then we have the real amplitude, and the real amplitude now has is a tree-level type structure. So it has just real scattering. Just a real function of our momentum, and that we can then write in terms of our spinors if we look at the amplitude, or just Minkowski products if we're doing a more traditional Feynman diagram calculation. And that's going to have limits that blow up as that corresponding to real physical configurations that are unresolved. So we call them soft and collinear. And we'll just look at what the definitions of these two are. So the one we'll look at first is a soft divergence. So this is when an emission of a gluon goes to 0. So we have some diagram like so. This is pi. Now when this momentum goes to 0, this thing will blow up. It goes to infinity. Right? Now the other type of singularity that we have is a collinear one. And that is when pi becomes parallel to what the quark momentum or the anti-quark momentum in our scattering here. So that would be where the gluon travels in the same direction. Basically, there's 0 angle of emission between the quark and the gluon, or the anti-quark and the gluon. So you see, this one can live anywhere. This is just the gluon can be anywhere in phase space and just go soft, so it has no angular constraints. And this one is constrained more kinematically by an angle dependence. Okay. So we're lucky. So if these things just existed, then we'd have a hell of a time calculating anything. But we're lucky in that QCD gives us very nice factorization properties of these amplitudes. fact gauge theories in general. So what they tell us is that, you can imagine both cases. So the soft case, the momentum goes to 0, right? I can just eliminate this gluon from my Feynman diagram, and I get left with something which looks like a four particle scattering, right? So I expect something which factors onto the tree level amplitude. Now what's the only difference between the true tree level amplitude and removing this gluon? What has it done? It's not a rhetorical question. Yeah, but in my limit, in my limit, I'm setting pi goes to 0, and so I'm really taking that limit, right? So we can, it's going to diverge, but I can factor it out. What is the difference if I just take this picture here and take the limit of this thing going to 0 versus never putting it in the first place? But it's all blowing up, and it's just going to factor, the kinematics is going to factor nicely onto the low point amplitude, so it's not kinematics. Color factor, there we go, right? Color has nothing to do with kinematics, right? I put the gluon in, it has a color, right? There's a TA that lives in here. Nothing to do with the kinematics, right? When I remove this gluon from a kinematic argument, I didn't remove the color, right? So that color is still there, and is necessary to preserve color when I square this thing up. And so what this is telling us is that when I'm worried about soft physics, I have to be very, very worried about what's happening with the color in my diagram, because that's still going to be there. So I have to worry about classifying all the different color configurations in the presence of my unresolved particle. The opposite is true for the collinear limit, right? Because when I move this gluon in with this one, I know how to pair these two up. So the color is always going to be a trivial argument there. But then it's the kinematics, because the spin of these two couples to the spin of this one here. So this one is easy kinematically, difficult from color. This one is easy from color, but difficult from kinematics. So life kicks you twice. All right. So let's have a look at that with our example. So we're doing E plus E minus, again, goes to Q bar G. And we wrote the amplitude yesterday in a enticing way. You may. Why does it appear of 1 over epsilon squared? Excellent question. So it appears because there's a region of phase space where I can do both, right? So I can be both soft and collinear, and so I get both kicks simultaneously, and that is what gives me the second pole. That's a good question. All right. All right. So we wrote it in this form yesterday because it makes the derivation of the soft function trivial for this process, but the joy is that this is the correct iconal factor that we always get. So this is our amplitude. We want to take the limit pi goes to 0. So in that limit, this thing in the brackets becomes momentum conserving, right? Because P1 plus P2 plus P3 plus P4 is equal to 0. And so this thing here becomes the real 4-point amplitude. And this thing here is my soft factor that depends on 3, 4, and 5. And the only thing I care about is the helicity of the gluon. So let me make a bit more room for this. This helicity. Yes, there's the helicities, always helicities. Charges and irritating annoyance. All right. So I was going to write this in a bigger notation. So I call this soft 3, 4, 5 plus times A for 0. Right. So this is my factorization of the soft limit, and this function here, soft 3, 4, 5 plus, is given by this here. It's called the soft function, or often also the iconal. Okay, so you notice that I suppress the helicity dependence of 3 and 4 because I don't care. This thing is invariant under flipping the helicities on 3 and 4, and only depends on the helicity of P5. And so there's another one which is soft minus. which is just given by the minus the conjugate one. So 3, 4, 3, 5, 5, 4. So, so these are the soft functions, and we see that they don't depend on the ellipses of the emitted particles. We do have to identify which particles it's going soft with respect to, right? Because that's going to allow us to handle the color. So in a more complicated limit, we have to sum over all the different ways of losing a gluon between our colored partons. This is another reason why we want to use color-ordered amplitudes, because then we only ever have a particle going soft between two well-defined color directions. So our general amplitude, so in QCD, our general factorization is given by, so for an n-point amplitude, we have some soft gluon between two partons. I don't care whether these are gluons or quarks. So what happens is we just replace the gluon by its soft iconal factor with the correct helicity assignment, and then we just have the amplitude with A and B next to each other. And because we color ordered it, these are the only ones that we get. As we go over the whole matrix element squared, we're going to get lots of different pairings because we do all the permutations of these sets. Okay, this is one of the advantages of a color ordered amplitude, is that it has nice factorization properties. Okay. Okay, so and it makes sense, hopefully, when we think about it as not depending on whether A and B are quarks or gluons, because we're effectively removing all the kinematics from the problem. So all that's going to be left over is some remaining angle dependence on where it sits in phase space relative to 3 and 4. So it doesn't matter what the spins of 3 and 4 are, or the specific partonic nature of them.
Soft one.
So it has to be. So it has to be the gluon. Well, there has to be if it's the quark, there is no divergence. So I don't care. Taking the soft limit of the quark just gives me 0. Yeah. So it has to be the gluon for our example. That's why it was P5. So it's a gluon at the next leading order. So and then it's just sandwiched between two colored partons. So in a color ordered amplitude, I always know which two partons are next to S.
So then for the first one, you had A5 and the 5.
Is between 3 and 4, right?
Isn't it? No, you've got 3, 4, 5.
Yeah, yes, but 1 is a lepton, so it isn't color ordered. So I don't care about it. So color ordering means that all my colored partons are in a well-defined ordering, right? 1 and 2 are not colored. So as far as the color is concerned, I have 3, 4, 5. Exactly, right? Because it's a soft limit with respect to color. The fact that that's basically telling me that 1 and 2 can't radiate a gluon, so there is no soft dynamics associated with them. So it has to be this, which means that this thing is between 3 and 5, right? So between 4 and 3. Good. All right. So that's soft. So then the other one we were talking about was collinear. And so in that situation we had, so we'll take 3 and 5 for our example. So we have that P3 and becomes parallel with P5. So our invariant S35 is P3 plus P5 squared, which is P3 plus lambda P3. So P5 is just some rescaling of P3, all squared. So this thing is just 1. So what happens in a collinear limit is that a single pair for next leading order, a single invariant goes to 0. So S35 goes to 0, but S45 remains non-zero. If S35 and S45 go to 0, that means that we're in a soft limit where we lose P5 is killing both together. So we have a single one that goes to 0. We don't normally parameterize it this way because this is making P3 special compared to P5. we're normally very pro-democracy, so we just pick some new momentum PC, which is, so we have PA plus PB, so this is for the collinear limit A and B become collinear. And then PA we write as ZPC, and PB we write as 1 minus ZPC. So PC is a light direction, and PA and PB are my two particles going collinear, and Z or Z is just our fraction of energy that's shared between the two. And we see if we add the two together, PA plus PB, we just get back to PC. Now you may be worried about why I've done approximately and not equals. In that case, you're definitely not a cosmologist. Congratulations. That was a joke. No, you may be worried because this is approximately true because we have to have a direction which specifies where they're going collinear with respect to. So we need another momentum that parameterizes an orthogonal direction, but we don't need that for this limit, so that's why I use approximately. It's true in the exact limit, but you'll see more complete answers written down elsewhere. Okay, so we want to see what happens to our amplitude in this limit. So we do, we can get the spinor limits by taking the roots of that result there. So the angle ones just go like that. And then similarly, the square ones are just defined in the same way. Okay, now we just put these into our amplitude and see what happens. So in the collinear limit of A5, 0 with 3, what do we get? So we have 3, our general amplitude is 3, 4, 3, 5, 5, 4, 2, 4 squared, 1, 2, 3, 4. All right, so we see this term here in the denominator, 3, 5, is what's going to be blowing up and causing our singularity. So we separate that one out, and then the rest of it is finite as we take the limit. So we write this as 1 over 3, 5. We keep that special. And then everywhere else we can put the limit in. So we put 3, we choose 3 is going to go like Z. And 5 is going to go like 1 minus Z, root Z. So then we get the 2, 4 is left alone. And then the 1, 2 is left alone. 5, 4 is going to become the square root of 1 minus Z for C. And 3, 4, where am I left? 3, 4 is cancelled with this 3, 4. So we're done. All right, so, okay, so now this thing here, 2, 4 squared, 1, 2, 4 C, is just A 4, 0, where we have 1, 2, C, 4. And then this thing here is 1 over the square root of 1 minus Z, 3, 5. So this thing here we call the splitting function, and that parameterizes how the collinear limit is approached. And the factorization is such that the 5-point amplitude factors into the splitting function times the tree level. Right? And this is another example of a more general result. The only difference we have to write down in our general factorization is that we have to allow for the possibility where there's 2 helicity assignments that are allowed for C. Right? So in this situation, C has to have a definite helicity because it's a fermionic direction. But in general, C could have both plus and minus helicity. So if we take a general n-point amplitude where we have A going collinear to B, we get the sum over helicities of our combined object A and that's the factorization that we get. So we have to classify all the different splitting functions based on helicity assignments, and they basically always have this form. So we can move on. All right. So the idea is that we understand how amplitudes in QCD and hence matrix elements in QCD factorize into the various lower order bit times the some universal function. So the nice thing is that we at least understand the universality of these infrared limits, and these types of functions here are what we're going to expect to find in the virtual and the leading order corrections. So that if we can integrate these things out over our unresolved partons, then we're going to get something which we have a chance of cancelling our series in epsilon in the virtual. So that's basically the strategy that we're going to use to eliminate infrared divergences. So in full QCD, it's extremely complicated. So we'll begin by looking at just a toy model where we have a simpler pole that we can cancel easily. So let's see, I want a nice, good-looking blackboard. Sure?
So by looking at that result, there's also another divergence if z goes to 1.
Yes, that's the soft singularity, exactly, yeah. Because they overlap, so I have to see it occur at some point. That is exactly the soft singularity. All right, good. Let's see, where's my clean blackboard under here? All right. So we're going to look at a toy model, which I lifted from the Black Book of Quantum Chromodynamics. So if you're interested in QCD, that's the recent textbook by John Campbell, Frank Krauss, and Joey, just as a first name. And he's a pet experimentalist, so he's on videos. And Joey is an excellent guy. So I certainly recommend that if you're interested, that you should get this book. It's updated with a lot of stuff, and it's pretty good. All right. So anyway, that's the end of the advertisement. So now that I've promoted, I can steal from it liberally. Okay. So we're going to introduce a toy model, which has a single infrared pole that we're going to cancel using different methods. So the idea is that we have a leading order matrix element. Yeah. Which we call Bn, so it stands for Born. And we can just assume that it's some constant for us. We don't really care too much what it is, right? It's a tree-level scattering that we've calculated, and it's finite. And then now we come along, we want to do our loop corrections in our toy model. So we calculate the one-loop diagrams, and we call it V, fancy Vn, which in our toy model, this is where we start to invent stuff, is just given by some constant over a single pole, and there's no finite bit at all. It's just this form here. And now there's a real matrix element too. And this depends on 1 degree of freedom which we'll call x. And this x goes between 0 and 1, and so x is in 0 and 1. And the divergence sits at 0. So this means that we can write our real matrix element in the form Rn x divided by x. So this is meant to be a fancy calligraphic R, and this is meant to be a run-of-the-mill capital R. This is a calligraphic V. I think it's beautiful, isn't it? It has.
What are the two V's?
So this is the calligraphic V, which we're never going to see after this.
I believe you haven't looked at
Yeah.
it.
Oh, what does it represent? I thought we were talking about penmanship. So what I went for was like a swirly bit here, and this was more of a vertical line in the V. So no, this is meant to be the total virtual, right? And here I've extracted the singular structure. So the calligraphic always means the total object, and then the regular lettering it represents the bit which can without the divergence. So this thing here is finite, and this is the epsilon goes to 0 is what diverges. This thing here is a finite function in x between 0 and 1, and it blows up when x goes to 0, like so. Good. And now we don't have to worry about the calligraphic ever again because it's impossible to draw neatly on the board. It's impossible to write neatly on the board, period. All right. Good. Okay, so that's our toy model. So you see there's only one single unresolved parameter here, x, which is obviously why it's simpler than QCD, because that, as we've already seen, has 2, and they overlap. But it gives us the idea of, it allows us to introduce the various methods that we're going to use to solve the infrared physics problems in a clear way, and then we can then use that language to discuss the real solutions. The real solutions to the physics problems, not the real matrix elements. All right. Not enough words in English. Okay. So, with all of our definitions, we can now write down the next leading order cross-section in our toy model. So the next leading order cross-section is given by the Born plus, for one last time, the calligraphic V times some mysterious function I will talk about shortly, plus the integration over the unresolved degree of freedom. Again, one more calligraphic R. Okay, so obviously what I've snuck in here is these Fs. You may be wondering what the F is going on. No, V is calligraphic V. So yeah, what is happening? These Fs are, they're going to correspond to measurements, right? So in the QCD language, when we upgrade this to full QCD, this means an infrared safe observable. So and this means something we can basically make out of jets, right? And we'll see repeatedly that this definition of the measurement is crucial to have any kind of meaningful next leading order definition, right? If we didn't have these in there, we could construct things where it just didn't make any sense in this order, right? So this thing is basically telling us that we have to ask sensible questions to get sensible answers. So we have to ask something which is infrared safe in our toy model. Just we'll see what that means in a second. But it has to this function here defines what we're measuring. So this could be, for example, in pure QCD, say we were looking at 3-jet production, right? Then this thing here would be my measurement of 3 jets, would define my jets through some clustering, anti-KT or something like this, and some separation to ensure that the jets didn't overlap. So they'd have some minimum PT and they'd have some minimum separation from one another. If I didn't have that, and I was just to run my matrix element, then I would have many singularities corresponding from when one of my 3 jets went soft and all that sort of thing. So we can think about these measurement functions here as something which defines a finite Born, right? So whatever this measurement is ensures this thing is well-defined and infrared safe. Does that make sense? Okay.
So what's the index, J? Or
J is the, basically because it's going to be made out of jets. So when we're thinking QCD, we think about this as a jet function. It's something which is going to define our final state in terms of infrared safe jets. So that's why it's kept. For now, we could just think about it in terms of N, right, as some number of scattering. Okay, so what does infrared safety mean?
Think of the X as some kind of Feynman parameter.
You can think of X as the unresolved degree of freedom, which is causing our matrix element to blow up. So it's a single unresolved parameter. So it could be, for example, the angle of the gluon, and the A going to 0 corresponds to the collinear singularity. And for us, for some reason, there's no soft singularity. So there's only one parameter which describes the divergence. So it's a single degree of freedom, which in our toy model is giving us the divergence. Okay. Any other questions? Yes? Why would I equal the cross-section to the amplitude? None of these are amplitudes. This is meant to be in terms of matrix element squared. Yeah, so we, in principle, this measurement function is including integration over all the phase space, and all that sort of thing. The whole process of this thing is not to compute something in the toy model, right? It's made up. The point of it is to show how these things have to talk to one another. So you can think about this thing as being maximally differential, and then maybe you're happy. Okay? Any other questions? Because this should be n plus 1, 2, right? Because whatever this thing is going to be this thing here should have an n plus 1, and then Rn is good. That was a good spot. So the n is like the degrees of freedom. So the real matrix element, no, it can still stay as n. It can stay as n. Because x is parameterizing my additional degree of freedom. So there's n degrees of freedom which correspond to my Born, scattering, whatever that is. And then I have one more which is corresponding to my real emission. So this is n plus 1 over here, because this thing, my measurement function can depend on my emission x and all the degrees of freedom that live in the Born phase space. Okay, any other questions / complaints? Oh, good. All right, This toy model is causing huge debates. Because we're doing some kind of BSM physics. Like, I don't know. Model building is where you guys love. All right, you're crushing me at it. Good. All right. So now we're looking at infrared safety, right? So we want to say, what is the constraints this function has to have that allow us to make a meaningful limit? So what had better happen is that as I take the limit at x goes to 0 of my increased measurement function, this thing had better go back to the born one. This defines an infrared safe measurement in our toy model. Okay? So whatever my measurement function is, it better satisfy this property. And for when we do real QCD, this will basically be the infrared safety arguments of jet clustering algorithms. Okay? Good. Okay. So now how can we cancel the singularities in this? How can we do something in our toy model to make a prediction for some observable so we can rule out the toy model as describing the universe? Well, at the moment we're in a pretty bad shape because this thing is infinite and so is this thing. So what we want to do is having some way of writing it in a way where we can cancel the singularities and have both things being finite so we can plug them into our computer and make predictions for our observable. So there's many ways you can do this. We are going to look at now at the simplest one, which is called phase-space slicing. And this will allow us to also make contact with NLO, which is good. So let's use this board over here. I guess I wanted some of the stuff on that board. All right. So getting rid of the calligraphic notation, we can expose our singularities. So there's one pole, and the next one is there, times fn plus 1 j of x. Good. Goodbye, spinners. All right. So we better start regulating this singularity. So it was never plus 1. I was going to make it plus 1 after the complaint, but then I realized I didn't have to, so I didn't. Yeah, that's my attitude to life. If I don't have to do something, I'm not going to do it, right? All right. So the reason being that this x dependence here is telling me that it's the additional dimension. So this is whatever in my model I have only my n degrees of freedom at leading order plus 1 in the real, which is given by x. So already this thing depends on the maximum degrees of freedom it can. 1 over x is parameterizing my singularity because I said that in this toy model, my singular region is just a pole at 0.
Over there's no 1 over x.
That's because that's calligraphic R, and this is not calligraphic R.
Okay.
It's just always all the complexities of QCD are about penmanship. It's about when you make that switch between calligraphic and non-calligraphic, which I guess is just called normal, and that really can, the angst and the debate that causes is just through the roof. So anyway, so I'm giving you my biases, which is that calligraphic is extremely hard to draw, but somehow this one still looks a bit calligraphic just because. Yeah. Anyway, moving on. All right, so we want to regulate this. Oh, do I have an? Oh yeah, good spot. Good spot. I was just seeing if anyone was going to notice. Yes, I did have an F missing. That would have been disastrous. Okay, so I want to do something called phase-space slicing. And the idea of this is super simple, which is why we're doing it first, as our first foray into IR physics. The idea is that the problem down here is at x is equal to 0. So I can isolate that by splitting the integration into a region around 0 and then above 0. Right? Super easy. So the first thing I'm going to do is regulate my integrand here. So there's divergence. So let's regulate divergence in real. And so I want to eventually cancel the pole and epsilon, so I better use epsilon as my regulating parameter here too. And so I just send this thing here goes to Rn over x, x1 plus epsilon. Okay? Now, this thing is regulated, and my divergence will appear as I take epsilon to 0 in exactly the same way as it appears here when epsilon goes to 0. So they can talk to one another now, which is good. And the Born I don't care about, so now I'm just going to look at the correction term. So I'm going to take these two bits here, and I'm going to call that sigma 1, which is the correction term. And then I can just drop the Born and all that stuff too. All right. So I'm going to split the integration into two parts. I'm going to get that border there, send this one up. And perfect. That one up, this one down. Everyone's happy.
You also regulate by having the lower limit of the epsilon?
Well, that's what I'm going to do with my slicing parameter. So this is just going to allow me to eventually write the two as the same thing. So that sort of yes is the answer to that question. That's exactly what I'm going to do. Okay, so now I'm going to write Vn j. So I split my integration into two. And then a second one. All right, so at the moment I've done absolutely nothing. Story of my life. However, I've at least got myself in a position where I could do something, which is also a good way to live your life. All right, so what can I do next? Well, now I can assume or construct basically that delta is much, much less than 1. I just made it up, so I'm free to do whatever I want with it. So I'll do that because that sounds like fun. This thing over here is finite. So I can just send epsilon goes to 0 and calculate that. Now all my worries are these two terms here. Yes?
How do you know that n plus 1 of x is finite under epsilon is 0?
How do I know that? Well, okay, so this thing doesn't depend on epsilon because I just regulated this.
Yes.
And I assume infrared safety over here.
Okay. I thought you were demonstrating the truth.
No, I have to. Infrared safety is something I have to mandate, right? I could define an observable which isn't infrared safe, and I would get nonsense. So it's crucial that I have this. Okay. All right. So yes. So I need infrared safety, otherwise things will never work. Okay. So that thing's finite. I could put epsilon go to 0. This thing is now what I'm worried about calculating here. So the idea is that if delta is really, really small, I can use the physicist's favorite tool, which is the Taylor series. So the idea is that I can. This thing is a finite function, so it has no more poles. So I can just do a regular old Taylor series, and I can approximate my answer. Rn of x, Fn plus 1, j of x is given by. All right. So I know this thing at 0 is just Fnj. And then this thing at 0 is just putting it at 0. Of course, this is an approximation. There's corrections that come in. Right. Happy? Good. All right, so now this is a constant. It can come outside the integral. So sigma 1 is Vn over epsilon plus Rn divided by nothing. So this whole thing is now in the same measurement function. Better have the integral. So this first term here is now combines with this one under the same measurement function. And then I get left over with this finite one over here, which I got rid of the epsilon dependence. Good. All right. Now you basically see, you're smart people, so you see I'm basically done, because this integral here is one I can do. Let's see how I get it so you can send that up so you see that and bring this down. Perfect. Yeah, we don't need this stuff anymore.
So far, it seems like, as far as infrared safety goes, all you really need to assume was that F finite.
Sorry?
It seems like more has been assumed in that condition than you need thus far. Can't you get away with just having F be finite in the limit x goes to 0?
But if it was finite, then these two wouldn't go together. It has to be the same to sort to the virtual. I mean, I guess you could you'll see in the end that when I impose the KLN theorem, I do something a bit arbitrary anyway. So I think I probably could build a model where this whole model worked, but I did that. But this is what happens in pure QCD. So I'm keeping the actual QCD-like nature of it. Yes, Nina.
I just noticed at some point we lost V sub n, and I'm not sure when or why.
V sub n. No, it's there.
B, not B.
B. Oh yeah, because I put an orange box around it, and I said we don't care about the leading order.
Ah, okay.
Yeah, there was. I used my colored pen. That was my artistic side coming out. Well, I thought that was the best bit of the whole thing, and then you just tell me that.
Clearly, I am sinful.
All right, I'll try to continue, but it's going to be difficult. All right. Okay, so I can do this integral here. So that's just going to give me a delta to minus epsilon divided by epsilon. So now I can put that in. So I get. I shouldn't have put it there. That was foolish. I get Vn divided by epsilon minus delta. Good. I think I've written this 1,000 times. I just called it a single symbol, so it would have saved me some time. All right, good. So this thing I can now expand in epsilon, and throwing away the bit that goes like epsilon, so I keep the pole and the constant. I get that sigma 1 is Vn minus Rn of 0 divided by epsilon plus log delta Rn 0 Fn of j plus all right, there we go. So we are done almost if we could impose some kind of theorem that told me that Vn had to equal Rn 0.
Is Rn 0 included inside that logarithm, or is it just log of delta?
Log of delta. It's coming from the expansion of this guy as a series function epsilon.
Have we imposed the specific reason why our epsilon from the virtual part has to be the same epsilon that we added for our x?
Oh, good question. So here, yes, right? So here we've implicitly assumed that we're making d less than 4, right? So you basically want to flip the sign between epsilon in your UV and IR formally. We assume that we've done all the, we had our general expression in terms of epsilon where we didn't actually specify, right? We did our UV renormalization, and now we're specifying that this epsilon is making dimensions smaller than 4. So, yes, basically.
Equals Rn, and you take epsilon to 0, does that the ratio go to 1 or 0, which goes faster?
So the idea is that this cancels first, right? So this thing cancels the pole is gone.
So
We've already
it goes to 1, or?
this thing goes to 0, right?
And epsilon goes to 0 more slowly?
Yes. Right. Yes. All right. So okay. This is. There's no reason why this has to be the case. Our calculation of the toy model works if this holds, and in QCD this does hold. It's called the KLN theorem. So the KLN theorem is telling us that if this is the case, then these poles cancel, and we're left over with two terms, which are both separately finite, and we can integrate them and make our predictions. Now, in QCD, we've already seen that these real limits factor onto the tree, right? So we can imagine that this is going to be the case because we've seen this type of factorization occur, and so then we just haven't seen any constraints on what the pieces of the virtual look like. But if we remember back to when we did our unitarity cut, we saw that the coefficient of the box looked like a tree too. So they are also to factorize onto the tree level amplitudes, and there's a hope that they'll cancel, and they do indeed cancel. All right, so in the end, we can write our final formula and for phase space slicing.
Sorry, is delta arbitrary?
Yes, that's what we're going to discuss right now. Excellent point. / complaint. So delta is completely arbitrary. I just plucked it out of the sky. I could have called it rho or sigma or alpha or beta, and I could have made you all calculate them. But yeah, it's completely arbitrary. So our formula is given by log delta. So I'm going to use my KLN theorem to write this as Vn. There's no real reason for that, just I like it. And then all right, so this thing here has solved our problem in that this thing is finite and this thing is finite. So I can integrate this in my n-dimensional phase space, and I can integrate this one in my n plus 1-dimensional phase space, and compare my predictions to data in my toy universe. So okay, but as I didn't see who complained because I had my back to the wall, but somebody hated the fact this delta was arbitrary. Good man. So it is indeed completely arbitrary, right? So we remember this isn't even an exact formula because when we did our Taylor series expansion, we dropped terms that go like delta. So we better make delta be very, very small, right? So this thing is a better approximation to our answer as the smaller delta gets, right? So point number 1 is that delta is arb, but should be small. For a good approximation. Okay. Point 2 is that the second term, so the real integration, is diverging as delta goes to 0. So delta should be big to avoid MC issues. All right.
Integral or the first part?
So this integral here is going to obviously go like a log of this to cancel the logarithm dependence here.
Oh, okay.
Right. So what happens is that we have this is delta on the x-axis. We have one that's going like this, and we have one that's going like this, and then the cross section when you add the two is independent of it. Now this is true up to some polynomial dependence in delta, so we better be in some region where this thing is close to 0. Right? This thing here is the true answer, but you see we have to calculate things we can't calculate to get there. Right? Oh, Monte Carlo.
Okay.
Or in some way you want to calculate this, right? You're doing an event generator because you want to make a differential distribution, and so if you make delta too small, this thing blows up and becomes hard to calculate numerically. Not necessarily hard to calculate numerically, but the issue is that you have to get it accurately, right? Because what we see is the classic problem in numerical physics, where you're trying to cancel two big numbers to get a small remainder. Computers, for some reason, hate this. You know, they go on strike all the time. So they're like, no way, don't make me do this, please. So they don't want to do this, and if you do make them do this, then you better make sure that they calculate the. So this one is which one are we doing? This is our Vn, say, and I want to make this one the real m. And make this one the Vn. So let's say that these two of these are, this one is just a formula, so we can just plot this. This one we're calculating with the Monte Carlo integration over x. And we better make this one be very accurate so that when we get the cancellation, we can get something which is accurate down here, right? So if this thing is of order 1,000 and this thing is of order 1, we're going to have to know this bit's better than 1 part in 1,000 to get a meaningful number for our cross-section, right? And the bigger you want your accuracy to be on your integration, the longer you have to run it for, the harder it is, and the more you have to be careful to parameterize your integrand in this region. So that's the big problem. So numerical instability is a big problem because you have two competing effects. Physics wants you to make delta be small, close to 0. Numerics makes delta to be large enough that you can do it in a meaningful way.
At no point did we ever have any functional definition of f. Like
No, I just told you that it was a measurement function, right? This is a toy model. I also didn't tell you V or R. I just told you they had to be related in the limit of 0. The point is this is how you do a cancellation in a model which tells you how to predict V and B. And in QCD, F, it corresponds to a measurement made on jets. So F of n is defined by a jet clustering algorithm. Okay. Good. All right, so we see that this method is not particularly good. Right? So so at next to leading order, these methods fell out of fashion. I should say, before I go into that, I should say why they are good. So I've said negative things. It makes it sound like I'm really being a downer on this method. But there's one thing which makes this method good, right? And that is that it's easy. We like easy things, right? The reason it's easy is that, okay, I get some kind of analytic form down here, which comes from my approximation up here, right? This is just this approximation here. So I have some approximate cross-section, which I work out once and for all. Then I have to calculate this thing. But this thing is just a tree-level type structure, right? So I basically reduced the complexity of my loop of my next order calculation to a difficult to integrate tree. So I've made my tree level really nasty by having to integrate it deep into some region where it's not wanting me to go. But I can do my tree level techniques, right? So the complexity of the calculation is essentially one order lower than the total calculation if I was doing something very clever, right? So the reason it's easy is that this is basically a tree structure. So these methods are easy to implement. And that sounds lazy, but as we go to higher order perturbation theories, this becomes a huge bottleneck. I.e., it's doable. Yes?
It looks to me like if you use that approximation, you can plug that into that integral, and you can get fn plus 1 equals Rn 0 fn divided by Rnx. If you plug that in, then all of the exponents other than 1 over x vanishes.
Isn't that what I did my below cut bit? That's this bit down here, right? This is only that thing is only true in this integral here where delta is close to 0. Over here, it's a completely invalid approximation.
Doesn't delta have to be the same on both sides? If you're just
Yeah, but okay, so it's true near the boundary, but near 1, it's complete garbage. You're trying to do some Taylor series well away from.
Delta. I thought delta was just your boundary.
I'm not running delta, right? But I'm integrating, and if I use an approximation which is inaccurate to some order delta, then I'm exposed to that inaccuracy massively up here, close to 1, right?
Okay.
I'm well away from my Taylor series being a valid approximation. So I could do that, but I would have a crap answer. All right? Good. All right. So anyway, so as I was saying, I was slamming this. Really hard to do numerically. Blah blah blah. There's a dependence on delta, which is unphysical. Boo. So these methods again. So that they fell out of fashion for next to leading order. So in the early 90s, they were popular because calculating next to leading order was hard. And then as computers and technology improved, they fell out of fashion due to subtraction-based methods, which we'll introduce tomorrow. But now they are somewhat back in favor at next to leading order because of this point, because they're doable. So I will give you a discussion of a next to leading order method that, for real QCD, that does this slicing, and then we can discuss that too. So what are the differences when I go from the toy model, which we've all ripped apart, to QCD? So QCD is more complicated. I was going to use the sponge as the pointer, which would have been comical. QCD is more complicated because there's more than one type of divergence, right? We saw this in this toy model. It was easy because we just had one, which was x, and we could treat it nicely analytically. The QCD is harder. So in my sketch here, we have some kind of z. It's like we can think of it as like a z decaying to q bar g. and this gluon is going to become unresolved in some limits. So as we argued before, if this one goes to 0, that corresponds to a collinear singularity. And if this one, I2, so there's another diagram where the gluon's over here, and if that one goes with that one, then they're collinear. That's along here, along the y-axis. And then if they both go to 0, so I1, SI1 and SI2 go to 0, then the I is soft, and that corresponds to the origin. So we have collinear along the x and the y, and soft is close to the origin where both the invariants are vanishing. Right? So the tricky part is, if I want to make some delta, so the obvious delta is like some kind of S min, so I just cut this bit out. So this is the whole real phase space up here, it's finite. All my problems are at the boundaries. So if I just cut this bit out here, and I cut this bit out here, and this bit out here, then I'm good, right? Because then I can just integrate this bit numerically, and I can get approximations for these bits here because I've seen the factorization of my amplitudes in QCD. So I know what the approximate amplitude is here because I just factorize my amplitude into a splitting function times the leading order. Similarly here, and here I know what it looks like because of the soft, because I factorize it into the soft function times the tree level amplitude too. So it seems like it's a solved problem. I have approximate formula for my amplitudes. I can put them in and integrate them. The horrible complexity is the fact that they overlap, right? As I don't want to double count, right? If I just did the collinear and then did integrate that up, and then if I did the soft, I would have counted this bit twice, right? The origin would get counted twice. So they overlap, and I have to disentangle them. So the obvious way to do it is just to put a diagonal cut across here, and then everything above it is collinear and everything below is soft, right? And at next leading order, you can do that, right? You can actually separate out the soft from the collinear. So you integrate the collinear down to some bit, and then you have the soft. You can disentangle the singularities in a fairly quick and painless fashion. At next leading order, this game is tremendously more difficult because at next leading order, we're going to allow two partons to become resolved, right? Because we have a correction where we can have this, and I can have a second gluon. And then when I have two gluons or a QQ-bar pair that are going that are unresolved, I have a whole range of possible singularities in my matrix element. I can have configurations where both the gluons are soft together, like a double soft limit. I could have where one is soft, the other is collinear. That'll be a soft collinear. I could have both being collinear to different partons. I could have both being collinear to the same parton. That would be a triple collinear singularity. And so you see hope that there is a tremendous increase in the number of types of singularities I'm going to get. And trying to find some way of disentangling them all is tremendously difficult. So in the last few years, there's been a clever way of doing this, which is to use, is there a question? Or just hearing things? Okay. So over the last few years, there's been a developments which have allowed us to make a slicing method that works at NNLO. And this uses the fact that I can write the below cut bit, so I can write this approximation here in a very clever way using something called soft collinear effective field theory, which is well beyond the scope of my lectures here, but hopefully will be at least touched in some way, if not explained nicely in your effective field theory lectures. But certainly you'll get the language of effective field theories if nothing else. So the idea of the basic idea of SCET is that it allows you to handle these overlapping regions in a clever way using effective field theory tools. And for us, that's all we need to know for now. So the question is, we're going to use so we have some ability to write an approximate cross section in the infrared unresolved limit, and we need some way of getting this delta type configuration, right? We need to know what is delta going to be for our NNLO calculation. And so my claim is that delta can be something called N Jettiness. What is N Jettiness? So N Jettiness is an event-shaped variable. So it's something which you calculate event by event. And it depends on, as the user, you get to specify N. So you can look for things like 1 jettiness, 2 jettiness, 3 jettiness. And you can broadly think about it of how much like an N jet event is this topology. So let me give you the definition. So we have lots of things to define. So we have Pi corresponds to a final state emission. So for us, at next leading order, we have two beams, PA and PB, and then we have potentially don't know why these are going in, they're going out. We have potentially 3 final state partons for a 1 jettiness. So we'll just think about a 1 jet event to make our lives easier. So this is electroweak stuff, and then this is a 1 jet event at next to next leading order in the double real. All right, now we have 3 ways of which these partons can cluster together to give us infrared problems, right? So we had situation number 1, where they all 3 go together. So I would cluster all of these 3 into 1 new jet. Right. That would be one configuration I could have. I could have a second situation where 2 go together. And one is left on its own. So that would give me this type of topology here. And this one, for instance, could have 2 partons in it, and this one would have 1. Or I could have all 3 separate. Okay, and now these 3 regions are going to have different types of infrared singularities that can occur. So this one here, so if I have all 3 together, can have all the worst singularities, right? Because if all of these 3 momentum are in the same jet, then you can have soft singularities where 1 or 2 of the 3 go soft. You can have collinear singularities because they're all traveling in the same jet together, so it's quite easy to make a collinear singularity. So you have triple and double collinear singularities all in there. So basically every type of unresolved limit is in configuration number 1. Now configuration number 2 has infrared limits, but they're not quite so bad, because the worst thing you can have is when this Q2 goes soft, so it doesn't form a real jet, but is not clustered with this one. And one of the partons in here also goes soft. So you can still have double soft singularities in here, but you can't have multiple collinear singularities because this emission is clearly at a different angle to these 2 in here. So the worst thing you can have would be, in a collinear sense, would be this collinear one in here and a soft one here. And then finally, all 3 separate, so this type of topology here, 1, 2, 3, there you clearly only can have double softs as the worst type of singularity you get because the collinear ones are separated. So the point of this discussion is to show you that how separated the partons are tells you something about the infrared physics that you can potentially have. Yes, Nina?
Like conservation of momentum, wouldn't it be extremely difficult to have double soft if all 3 are separate because they're completely different angles?
No, because I can still have the limit where I have this guy to recall at whatever I want, right? So I have something where this one comes in, this one is a hard direction, and this one is soft, and this one is soft, and then it's just balancing against the electroweak particle. Yeah, there's no just exclusive 1 jet production in LHC. There's always something that's balancing. So we have our electroweak thing here that isn't really relevant for the discussion. It's just playing the role of momentum conservation and easing your concerns. Good. All right. So the point of this discussion was to show you that the separation of these objects into different topologies based on how separated the partons are after clustering gives you an ability to classify the types of infrared physics you're going to get. And so that's where this N jettiness is going to come into play, because N jettiness is a measure of saying how a 1 jet-like the event is. So this one up here is going to be extremely 1 jet-like because there's 1 jet balancing exactly against an electroweak boson. So this one is going to look exactly like a 1 jet topology. This one down here may not, because if this emission is big enough, it really has a 2 jet type structure, and so this one here is may or not have a 1 jettiness type configuration, and so on and so forth. So I think I've said enough as I can without actually giving you the definition mathematically of N jettiness, but these pictures will help us understand it.
So can you not have the same number of jets, but also have a glue line emitted from one of the final states of partons collinearly, so that you sort of have just collinear jets or something like that?
So hang on. So you want me to do? I have incoming. You want 2 in the same jet?
Well,
Yeah, that would, so these two collinear with P1 would reside in this type of topology. Right? If they're collinear, I'm naturally going to cluster them together into one jet. So these topologies are always after clustering. Right? So if I looked inside, I've got some diagrams for this in a minute. So can I postpone? I can postpone answering your question for a couple of minutes, and if you still have it, we can come back to it. Okay, good. All right. So what is one jetting? Okay, so the jettiness of a single parton is defined as the minimum of I is equal to A, B, and 1 of Qi dot Pj divided by Qi. Loads of stuff to define in this equation here. So Pj is one of our final state partons. So this is, we choose one between P1, P2, or P3. Right? So that's something which is done at the partonic level. Q is after clustering. So after clustering, we're going to have one jet. And we make it into a one jet by taking only the hardest jet. Right? So Q, for us, for our one jettiness, Q, we have to be careful because we also can go with the beam, but the final state one is the hardest jet. So hardest jet plus beams. So these are the things that survive after jet clustering. So that's Qi. So that's why it goes over A and B, which are the two beams, and 1, which is the jet, which we take now to be the hardest object in the event. And this capital Q down here is an energy scale, which we can define as the user. So different definitions correspond to subtly different definitions of N jettiness. And for us, we'll just take the fact that Qi is just going to be twice the energy of the jet. And it's a hard scale in the process. It doesn't really affect the infrared discussion that we're going to have. So the important thing is that it's these dot products here between clustered momentum and the partonic level. So that's for a single parton. So then the total event shape N jettiness is just given by the sum of the number of final state partons that we have. And my claim, which I'll try to prove to you now, is that this thing can play the role of delta in our slicing discussion. Okay. So my claim is that this thing plays the role of delta. When tau 1 is close to 0, we're in some double unresolved regime. So we're in some regime which is pure double unresolved limits, when i.e. has all the complexities of next and next leading order. When we're in some regime where tau 1 is greater than 0, then we are in a single unresolved limit, and we have something which looks only like next leading order. Right? That's the one order up higher equivalent thing of what we did at our toy model, where we did next leading order was written as something approximate in the true NLO infrared limit plus some correction which just looked like a tree level guy. So this is exactly the same thing, just done at next leading order. So my argument has to show you that tau 1 of equaling 0 corresponds to all double unresolved limits, which hopefully will answer your question. All right, so let's look at what can happen when tau 1 is close to 0, right? So we take some partonic configuration, P1, P2, P3 as drawn. We cluster it as argued into a topology. Now, if they're close to 0, right, then basically all of our dot products are going to have to be small. So here, in this configuration here, I've drawn them, I think, in the way you were maybe talking about, where everything is collinear, right? So this type of example here will be close to 0 because P1.Q1 is small because they're close in angle. P2.Q1 is small because they're close in angle. And P3.Q1 is also small because they're close in angle. So this type of configuration here corresponds to double unresolved limit, which will be triple collinear. But you see that actually this diagram can capture quite a few of them as well, because these could also be soft and all that sort of stuff. The only thing that's not shown sort of in this cartoon is that I could have wide angle soft. But then Q1 basically goes back into the, this tau 1 is still 0 in that limit, because if I take the soft limit, then the pk here is always going to 0, and that kills it regardless of where it is in terms of an angle. So basically what happens is that if tau 1 is 0 or very close to 0, then you're losing 2 invariants or up to 4 invariants here, and hence in a double unresolved limit. So clear, unclear, moderately clear.
I guess what I had in mind was more like
Yes. So you want me to move P2 down to be coming off P1?
So now there would be 4 final states. I'm just imagining the limit in which you can have the last. But if it's soft and collinear.
Sure. I mean, so my claim. So that's an allowed limit. So if I had this gluon. So say I didn't draw it all. I mean, this sort of not a Feynman diagram. It's just a sort of mess to show you stuff coming out. But if the configuration that you're describing is, say, this gluon splits here, so I have a tree where there are 2 of them coming off here, and there's another one that's spectating, you would say, okay, this could be collinear here, and this one could be soft. Sure, that's a double unresolved limit. Right? Any way in which I can lose 2 gluons is a double unresolved limit. But my claim is that you'll kill enough terms in here to make it be 0. Right? So any double unresolved limit, and you can do it as an exercise later on, will correspond to tau 1 of equaling 0. So that's okay. So hopefully I've convinced you / hand waved my way through and shown that tau 1 of equal to 0 is corresponding to exactly this configuration where we have a hard jet exactly balancing the electroweak physics, and we have a pure Born-like topology. So it looks just like the leading order. Of course, at leading order, it's manifestly true that tau 1 has to always equal 0, because at leading order, a single parton becomes a single jet, and this thing is always 0. Right? Good. Okay. So, so that's the double unresolved limit close to 0. So then the last thing I have to do is convince you that when it's not 0, then you can only have at least 1 unresolved limit. So, for example, a situation where it's not 0 would be where you have these 2 clustered together to make a single jet, Q1, that's the hardest one, and P3 sticks out here, but is basically not soft enough to put us into the tau 1 equaling 0 regime, so there is some recoil here between this non-zero balancing between the jet and the electroweak physics, which is of course allowed for jet observables, not partonic, right? So that's the configuration that we have. But then when we put it in here, we see that Q1.P3 is not small, right? So this thing here will give us some non-zero tau and push tau to be bigger than 0, which means that we have a clear case where we can't lose 2 partons. We can still lose 1, right? We can still have that all of these make a small tau, right? So we can still have a single unresolved limit, but we don't mind that because that's just going to be our above cut bit, which is going to be a next leading order calculation. So a single unresolved limit we can handle because that's exactly the next leading order calculation, and that's fine because we just do that with next leading order technology. So we separate tau based on 2 bits, close to 0, bigger than 0. Bigger than 0 becomes the next leading order calculation. We can do it with all the technology we discussed, unitarity, with the stuff we'll discuss tomorrow, which is subtraction. We can calculate the next leading order efficiently. And then the below cut bit we have to now worry about, right? So at the moment, I'm still tricking you because I've said this event shape variable is great. It separates the phase space into a double unresolved limit and a space and the thing which can have most single unresolved. So I can do a slicing approach on it, which is fantastic. But I haven't told you how I can get an approximate answer in the below cut bit, right? That was the other important thing I had to do for phase space slicing, where I write down an answer which I can use as an approximation. So that is coming from Sket. This is the bit I was saying about Sket before. And so Sket tells us how to do this. So this factorization theorem was proposed by these chaps here. And they say that if tau is small, so if our N jettiness, so now we relax the constraint, there has to be 1 jet, there could be multiple jets in this factorization formula. So if this thing is now basically exactly like delta was in our previous example, so the cross-section integrated in this region close to delta close to 0 can be factorized into these objects here, plus some correction, which is the approximation that we're making. And so these various bits here are the beam functions. So these calculate collinear radiation that gets absorbed into the beams. There's this soft function here, which is a matrix in color space. So that's the most complicated bit of these universally sketty things. This J thing here is a jet function, which describes final state collinear radiation. And finally, H is the hard function, which is process specific, and that would be what you're trying to calculate: Higgs plus jet, Z plus jet, whatever you like, Higgs plus 2 jets, that sort of thing, right? That's the process specific information, which is now renormalized such that it's infrared finite, and this is just a finite function with no infrared limits. So how to calculate this is well beyond the scope of these lectures, but the point is that they have all been calculated and can be expanded up to next in order accuracy. So the beam functions are calculated, and the jet function some time ago. The soft function for one jet's more recent. I should advertise that this is one of you guys is this person, and I'm probably giving a student talk on it. So you can ask them multiple questions on the soft function. Good. All right. So then my remaining minus 2 minutes. Remembering that I actually borrowed 10 minutes yesterday. I'll show you some example calculations that we can do with this type of method, right? So this is basically our dependence on our cut for a whole bunch of known processes. So this is taken from MCFM. This is one of my advertisements. And we see for Higgs production at the top, Z production, W production, and then associated Higgs production for Z and W. So all of these processes are effectively 2 to 1. And so they've been calculated analytically in the historical context of the inclusive cross-section. So we know the inclusive cross-section GG to Higgs analytically, so we can then compare the result obtained with slicing to the analytic results. So this ratio here is the numerical result divided by the analytic result. And there's what's not shown on the plot is that there's this huge cancellation between log to the 4th terms. So for next leading order, we get something which goes like log tau to the 4th. Between the below cut bit and then the above cut bit, correspondingly supplying the other cancellation to get this polynomial dependence on tau cut that's left over. So what we see is that it works, in that the correct limit is approached in every case. And we see that tau has to cut to be pretty small. So this thing is actually so this thing has a dimension, so it's a bit, so it's not a dimensionless number like x was in our previous example. This thing is in GeV. So we see that this has to be 10 to the negative 3 GeV to get in the region where we get something which is asymptotic. And if you were out here, then you would get a pretty ropey prediction. So what's not shown is the time it takes to get the various points. So you would say, okay, I don't really mind because I can get it down here and it's pretty good. I don't really care that it's easier for me to calculate up here. The point being that this takes a lot longer to run, right? So I can't remember the exact numbers, but these points up here you could probably do in an hour or two easily. In this point down here, you're talking more a few days, right, to get the same level of Monte Carlo accuracy. If I ran it for the same Monte Carlo input, so the error on this bit stays more, then what you would see is these points get bigger and bigger numerical uncertainties to the point where this thing down here has a huge uncertainty. So that's anyway. So, but the point is that these things, this method works, and it's doable. The next leading order physics. So tomorrow I will tell you about subtractions of how you do a subtraction method to handle your infrared divergences, and we'll do a quick example calculation ourselves, so you see it working, and that then I can advertise even better methods of doing next leading order. So I guess there's questions.
Is the solid line just to guide the eye, or is that something?
Is the solid line to guide it? The solid line is a fit to, so we can estimate what the dependence on the corrections should be, right? So for example, we're doing our Taylor series, we think it should be linear, right, in delta. So we expect as we get small enough that we should see a straight line in our Taylor series, right? And then as we got further away, it'd be quadratic. Now this is a little bit more complicated in that the dependence does not go simply like a polynomial in tau n, but goes like tau n log tau n. So this thing is a fit to things which formally go to 0 as tau n goes to 0, but we can estimate what the structure should be. And you can actually calculate some of the leading corrections. So that's there's a big industry now to do this, because as you do that, you improve the method by adding in bits that you missed. So that's an industry now, is to try to improve this method by adding in new terms. So that fit is it's just a fit to the data or the calculation results, assuming this type of the polynomial dependence. So you see, we can get it. We understand what the form of these corrections is, even if we don't know the exact analytics. Yes. For initial, the initial state is included in the fact that it enters into the definition here, right? A and B. So you can allow radiation to get sucked into the beam. So it is in there, right? But yes, and that's absorbed into the beam functions. So it is in there, right? So yeah. Any other questions?
Question, the collinear ISR is just absorbed into the beam?
Yes, you can think about it as redefinitions of the PDFs, right, basically. But in such a way as to disentangle the soft too. It's complicated, but clever. Any other questions? All right. Then, all right, I think I saved 3 minutes over the 2 lectures, so that's